In this video, we're going to work down to a technical definition of the directional derivative, and then try, as we did with regular derivatives, arrive at a simpler formula that will let us compute the slopes in arbitrary directions in a fairly straightforward way. One challenge in dealing with directional derivatives is the number of pieces involved. We can take a look at that and see that relationship or that complication by looking at the formula. When we look at the calculation required, we have a derivative, symbolized by a d. We have a direction, represented by a vector u, and we have a function that would be defining our surface, and we also have a point. So the formula is by necessity going to involve all of these in some way, and well, let's work our way back up to arrive at that. The first element is the direction that we're traveling in, or the direction we're looking in, and we're going to represent that as a vector in two variables, u1 and u2. We're also going to require that it be a unit vector. The idea being we just care about the direction that we're facing in and not so much about the magnitude of facing in a certain direction. That doesn't have as much meaning here. So we are going to enforce that whatever vector we're working with is length 1. Okay, well that defines a boundary on the u vector itself. Its length is 1, or the sum of its elements squared equals 1. Then we're at a certain point AB, we have the function f, and then we're asked to compute the rate of change of f in the direction of u, and it will be given by this formula here. I'm just going to highlight the a's and the b's, so that's a reference point. Then we're going to include the u1 and u2, and effectively what you see here is that we're going to have an h multiplier in front of both of these u1 and u2s. I'm going to erase these again so we can see all the characters, but we have u1 and u2 times h. And the idea is that we have this vector, u1, or u rather, it's based at the point AB, so we use that as our anchoring point. And then what we're going to do is gradually shrink the step that we take as an h multiplier times u1 and u2, and that effectively shrinks the vector until it becomes smaller and smaller and smaller, and then we evaluate the surface there. If you think in 3D, then what we're talking about is the point above the surface here, and we take a small step and ask what the height is at that small step later in the direction of u. Last step is to turn that into a slope. Notice the numerator here is a change in f values, and if we're talking about h being the multiplier for this vector, it is actually equal to our step size as well. Our vector is length 1. If we scale it by h, then we have a step of length h, and so we have delta f over h, or we can think of that as delta f over the step, and here we can't really encapsulate it as easily. It's a step in xy. It's the distance that we're going to travel, and then we evaluate the height of the function at the 2 points there, and we're going to let that step size approach 0. And that's what's going to give us an instantaneous slope in the direction that we're talking about. Nomenclature-wise, this is what we call the directional derivative of our surface, of our function f, at the point AB in the direction of u. It's sometimes notated with this capital D to indicate derivative. It's also sometimes notated in a way similar to our subscript x of AB, that would be the x direction derivative. Well, you can just replace that x with a specific vector u. An important note again is that this only applies, this formula is only correct if we have u being a unit vector. So having this length 1, that's what turns the length of the step in this diagram into 1 times h, and so dividing by h makes things work out correctly, makes things turn into real slope values. Now there's zero shock here that this is not the way we're typically going to evaluate derivatives in directions other than x and y, because this is the limit definition. This is where we go back to if we need to, but we'd really like a more efficient process that uses all the tips and tricks that we have about derivatives from our earlier work. So let's take a look at that next. We are interested in computing these directional derivatives in a systematic way, and we have all of these ingredients that we just talked about. We can then take this formula, so applying the definition here. If we apply the definition of our directional derivative, it's this limit as h goes to 0 of, notice carefully the comma in here, this value and this value plugged into f minus a and b plugged into f. And what we can do is simply define these two things here as x and y for a second. Not unreasonable. This is an x coordinate. This is a y coordinate. Let's go for it. Now we can take advantage of some of our earlier work with local linearity, which gets into the difference between the function at some point near another location. Well, that's perfect. F of xy minus f of ab is going to be approximately equal to, going back to our linearization formulas, the x slope at the point AB times x minus a plus the y slope at AB times y minus b. This corresponds to our delta f equals the x slope times delta x plus the y slope times delta y. It's one of the earlier forms that we had for our linearization formula or tangent plane formulas. Well, that's interesting because now we have something that relates back to the derivatives we do know how to take, the x and y partial derivatives. Let's explore a little further. All right, well, our directional derivative in the direction of u at the point AB of the function f is equal to the limit as h goes to 0 of, well, what we just said on top there, let's go back one step. We had this expression here, and we can replace it with our tangent line formula. So we can replace it with the x derivative at AB times x minus a plus the y derivative of AB times y minus b all over h in this case here. Let's go back one slide. We're replacing this. The numerator is exactly what we wrote here, and then we're copying over the h from the denominator. All right. Well, now we want to evaluate what happens when h gets small, but we don't actually have the h in our numerator yet. Though it's hiding in there, if we remember how we defined x, x was a plus h times a, or h times u1, the direction of our vector that we're going in, and y was b plus h times u2, the other element of our vector. And so we'll just bring this down a hair so we have some room. We are able to replace now the x value with its expression here. And you can see already x minus a, but x has an a in it. This is going to get good. ab times x, which is a plus b, a plus h u1, and then minus a, plus the second term, the y derivative, a of b there, and now y is b itself plus h times u2, the direction of the vector in the y-coordinate, and then minus b. And of course, we see that cancellation that we mentioned earlier. And so we get the all over h, can't forget that. Copying that from the earlier term. Then we have the limit as h approaches 0 of, well, all of this goes away. We have the x slope at AB, we have a u1, and we have an h. We'll bring that up front. We have the y slope at AB, we have u2, and we have an h as well. Bring that up front. Why do we do that? Because then we can cancel all of these h's. Both numerator terms have an h, and there's an h in the denominator. Now, if those just go away, turns out we don't really need this limit. The reason we need that limit is because this is an approximation, and this approximation gets better and better as h approaches 0. But at the end of the day, what we get is the x partial derivative times u1 plus the y partial derivative times u2. Now, what do those pieces represent again? Well, these two elements here represent the surface slopes in the x, and let's be clear here, the positive x and positive y directions. And that is then combined with where we're moving in. So if we were to move in the positive x direction, we'd get this slope. But we're also moving a little bit in that x direction, which is represented by u1. And then we also multiply or add in the effect of the y slope multiplied by how much we're moving in the direction y. So these are the components of our travel direction. And this has almost an identical flavor to what we saw with the linearization. If we want to know how quickly our function's changing, we look at the slope in the x direction and then figure out how far we're moving in x. We take the slope in the y direction and look at how far we move in y. The amount of movement in the x direction and y direction are captured by u1 and u2, because that gives us, going back to slider 2, the direction that we're traveling in this calculation. So if we're asked for the partial derivative, we're going to calculate the two partial derivatives that we know already. So I put a big check mark there. And then we include the effect of, well, we're not going in the x or y direction specifically. We're going in some combination of those two directions represented by the vector captured in u1 and u2.